Electron affinity. So this is not electronegativity, this is electron affinity, and this is adding an electron to a gaseous stable elemental atom, right? So just some element that's a gas, and we're adding an electron to it. This process will either require energy input to make happen, or it's favorable and will release energy, right? So there's two things that can happen. In general, the more favorable this is, the more energy that's released. Okay, so the more this wants to happen, the more energy is released. And we'll talk about the trends on the periodic table for this real quick. So electron affinity goes down as we go down the periodic table. Okay, and this is due to increased distance from the nucleus, right? And there's more shielding that happens. So as we go down the periodic table, let me pull the periodic table back up. So as we go down, chlorine is going to pull has less affinity for electrons than fluorine does, right? Elemental chlorine has less affinity than fluorine because there's more shielding from the core electrons in chlorine than there are from fluorine. Okay, and it goes up as we go across a period in general. So fluorine has higher electron affinity than oxygen, because it's got a higher effective nuclear charge, right? There's more protons pulling on the electrons on that free electron than there is for oxygen. Okay, don't say again that it goes up for fluorine because it's to the right. All right, I don't want to see that. I don't want to see that it goes up for fluorine from chlorine because it's above chlorine. You need to talk about shielding here, right? Chlorine has more shielding, so it can pull on that free electron less than fluorine. And you need to talk about effective nuclear charge between oxygen and fluorine. Okay. Now there are some exceptions, and we're going to cover those exceptions really quick. So these dots so first of all, it's only showing the ones that actually pull on this electron. It's only showing the ones that this is a thermodynamically favored process. These lines indicate these are adjacent on the periodic table, so oxygen's next to fluorine, and we can see that fluorine pulls harder than oxygen. All right, nitrogen actually requires, so let's talk about, we notice carbon pulls on electrons harder than boron, right? But for some reason, nitrogen requires energy to push an electron onto. And again, this is electron-electron repulsion, right? So carbon, if we draw the p subshell, right, the p orbitals, carbon looks like this. And it's going to pull on a free electron, right? It's going to release energy if it gains an electron because that electron can go in here, right? So that's carbon minus, right? Those three. Okay. Nitrogen already exists as this state, right? So it won't pull on an electron because the electron can only go in next to another electron, and that increases the electron-electron repulsion. So that prevents nitrogen from really pulling on free electrons, right? You're going to have to force that electron in there, so that takes energy. Okay. Oxygen to fluorine, right? We just talked, that makes sense. Fluorine has higher effective nuclear charge. What's weird, you'll see that sodium and lithium are on here. So sodium and lithium can gain an electron. Remember sodium and lithium, so here's lithium, it's got the 2s, and it's got one guy in the 2s, or one electron in the 2s orbital. It actually can fill that second one in there, and that does release some energy for it to happen, but it can also completely get rid of its 2s electron too, right? And that releases energy. So sodium is, the kind of alkali metals have some weird behavior sometimes. Okay, so if we look here, aluminum to silicon, right? Silicon releases more energy than aluminum does, right? And let's look at where silicon is placed on the periodic table. So silicon's here, right? It releases more energy than aluminum does when it gains an electron, but if you notice phosphorus releases less energy than silicon, and that's the same exact argument that we just made between nitrogen and carbon, right? Silicon's electronic configuration, so this was 2p, I should say. Silicon here is going to be 3p, right? That's its valence electrons. And silicon exists in this state. To make silica minus, silicide, I guess is how you'd say that, you add in an electron over here. Okay, phosphorus already exists as this state, right? Now, it does release a little bit of energy, so it does want an electron to go in here, but it releases less than silicon does because of this electron-electron repulsion. And you notice sulfur releases more, even though, so let's draw sulfur. So, or sorry, this is phosphide, right? Okay, sulfide. Let me, hold on, I'm getting ahead of myself a little bit. So now this is sulfur's electronic configuration. Okay, sulfide would be this, all right, and because sulfur has a higher effective nuclear charge than phosphorus, as we said, it's going to pull on that electron harder and release more energy. So that's the trend. All right, there's some explanation stuff down here. You can read through it if you want, but I just want you to know that that free electron is more easily absorbed as we go to the right because of effective nuclear charge, and it's less absorbed, right? It doesn't give off as much energy when it's consumed when we go down because of shielding, right? And then I want you to know the exceptions. Those are due to electron-electron repulsion. Okay, I'll see you in the next video.